Great. So hello everyone, I'm Chandra. I've been talking about 3D bioprinting for quite a while. So in today's session, we will talk about yet another type of bioprinting modality, that is light-based bioprinting or light-assisted bioprinting. The third one, if you remember from our previous sessions that we talked, that there were almost four modes of bioprinting. So now we are going to discuss about the third one. So the first one, second one, the extrusion one, and the droplet one, they are the most widely used bioprinting modalities that you will find in labs. It is because mainly they are easy to understand. The systems that come, they are moderately cost effective. Like you can purchase it, you can think of purchasing it, easy to tinker with, and that is why they are much more user friendly for people's use. So that's why we discussed more in detail in the previous sessions only about these two techniques. While the other two techniques are like not much people know about it. Okay, even the professors who are working in this area, they are not keen to explore much because mainly the systems are very expensive because of the use of lasers and all. Okay, so that makes the handling process bit more complicated. So you need to be trained well to use these machines. But yes, it has their own advantages and disadvantages that we should know in theory. So in case you were to work in a project where the use is where the demands can be fulfilled only by the usage of these machines, then you should know the background of the techniques. Okay, that's why we are going to discuss these light-based bioprinting technique. So we are today going to discuss this one, light beam induced 3D printing or light assisted bioprinting. Like it has several names. All right. So I'm going to use the name light assisted bioprinting for today's session, or LAB in short. All right. So why this technique? Why do you want to use this technique first of all? How is it better than the existing ones that we already discussed, like the inject one, the extruders? How it is better than that? First thing is, since there is no use of nozzles or needles, so you avoid the issues of clogging by using this technique. And clogging can arise due to multiple reasons, like viscosity is high, or cells have agglomerated with each other, or the bioink that you're using has a higher tendency to get dried up, so it can get trapped in your aperture, needle or nozzle aperture. So because of that, clogging can happen. So if you want to totally avoid clogging, all right, because of any of the reasons, then using this light assisted bioprinting can be beneficial. But what happens here? Okay, so a simple definition about this technique is, it's a technique capable of trapping multiple cells. All right, this is a technique capable of trapping multiple cells in laser beam and deposit them as a steady stream on arbitrary non-absorbing surface in a matter of seconds. So basically what it does, there is a bioink containing cells, and on top of it some laser beam is projected. All right, through this laser beam we are able to trap multiple cells together in form of a droplet, and that droplet can form can get formed as form of a jet or a single droplet at a time, depending on what parameter you're using. So there are multiple parameters related to this technique that will come up, that we'll understand later on. All right, so depending on what parameters you're using, you can create a jet, let's say jet of droplets, and it gets deposited on a substrate, on a receiving substrate, and depending on where it is falling, you can create a 3D structure. Okay, and all this happens in matter of few seconds. That's it. So it's a very fast technique. I'll discuss about how the trapping of cells and all happens through schematic and later on. All right, actually in just the next slide it is there. So the system, the laser assisted bioprinting system, it consists of three key elements. So let me show you this image. So this is the system that I'm talking about. These are the three elements here, right here in this area. If you can follow the laser pointer, this is the area where the three key elements are there. All right. There is a first a transparent glass substrate. All right. This is called the support. And on the support, we coat a layer of bio ink. Now, bio ink consists of cells, media, or whatever, right? Maybe some biopolymer or something like that. You can mix in your bio ink. And in between the bio ink and the support, there is a laser absorbing interface layer, all right, in between the bio ink and the support. And whatever drops containing cells that are formed out of the bio ink, that gets deposited on a substrate. So these are the three key elements. Apart from that, there is a laser, all right. That laser, with help of mirrors, it can scan in XY direction, all right, at some velocity. And there is a lens as well that gives that has some numerical aperture, all right, that helps in focusing the laser at a particular point in XY plane. All right. So this is the entire setup of this laser assisted bioprinting. Just let me quickly go over the points now. So I told you there is a laser, then there is a ribbon. So this entire thing is called ribbon. And ribbon itself consists of three parts. This is the ribbon, this is the substrate, this is the laser. The ribbon consists of the support. All right. This support is transparent to the laser. The support is coated with a laser absorbing layer. All right. And this laser absorbing layer in turn is coated with the bioink containing cells. All right. So the support that we are using is transparent to the laser radiation wavelength. All right. So all the laser can pass through the support. Whereas the laser absorbing interlayer, it is necessary, it is very important for basically droplet formation. All right. The droplet that you're getting, it won't happen if you don't have this absorbing layer. You will understand why in the later slides. All right. And what it does also, it doesn't allow the bioink or the cells in the bioink to directly get in contact with the laser. So laser induced or light induced cell damage is minimized by the presence of this absorbing layer. So it allows around, so 1% of the incident beam is absorbed by this interlayer, whereas 99% get transmitted. That helps in basically formation of these droplets. And then there is the transfer layer or the bioink. So this is the ribbon. Again, I'm repeating, this is the ribbon. Ribbon consists of the support layer, which is transparent to the laser. Then it contains a laser absorbing interlayer. All right. It eliminates what is a direct contact between the bioink and the laser. It is necessary for this droplet formation. I'll come to that point later as well, how it is necessary, why you need it. I'll come to that later. And below this laser absorbing layer, there is a coating of bioink. This is also called a transfer layer. So this entire region is called the ribbon. This is the substrate onto which the droplet containing cells will be deposited, and this is the pulsed laser source. So please note, the laser that we are using is pulsing at some frequency, like continuously it is switching on and off. So that also helps in conserving energy, and also it doesn't allow direct or long it doesn't allow long-term exposure of light for as it can be harmful for the cells. All right, so it is pulsing continuously, it is pulsing, and we can pulse it at some frequency. So what is this laser absorbing interlayer is made up of? First, it's quite a thin film. Its thickness is in the range of tens of nanometer, say 10 nanometer, 20 nanometer, something like that. Means it's very thin. It is usually made up of metals like gold, titanium, silver, or some metal oxides like titanium oxide, or some polymer like triazine. All right. It has been shown that through experiments that whatever volume of bioink that you deposit, it is proportional to the laser energy that you're using. Okay. And for the droplet to form, you have to cross a minimum threshold laser energy. If you stay below the threshold value, the droplet won't be formed. Also, please note the laser type that we are using has a radiation in the range of UV and IR. All right, and the energy of the lasers is quite less. All right, sometimes milli or microjoule. So it's very less energy. But another the same point that I'll repeat again is the energy of this laser determines how much the volume of the droplet will be ejected. And for the droplet to form, one should cross the minimum threshold energy. Then only droplet will be formed. Okay. So in the boxes, they are showing some key parameters that can affect the process. So we already discussed the laser type, right? You can use UV and IR. The repetition rate or the pulse rate also affects the process. Then you can use lens for focusing. So the numerical aperture or the size of the pinhole through which the laser will pass, that will also affect how much energy is going to fall on this ribbon. The scanning mirrors determine how fast the laser will scan on the XY plane over the ribbon. Environmental factors can also impact the process, like the temperature, moisture, all right. Then the substrate properties can also affect the morphology of the droplets. Properties like the wettability, how hydrophobic or hydrophilic it is. If there is some coating, then how that coating can make the substrate soft. So when the droplets will land on the substrate, it will get a cushioning. So there is less chance for the droplet to disintegrate or splash on the substrate. Then how much is the gap between the ribbon and the substrate? That will also impact the morphology of the droplets. And of course, the properties of the bioink that you already are aware, like the cell density, viscosity, all right. But here you see two more properties of the bioink that can impact the process. One is the thickness, how thick this layer of bioink is coated onto the ribbon first. And second, the surface tension of this bioink. Because for the droplet to form here, the surface tension plays a very important role. Surface tension basically, if you want to imagine what is surface tension, it basically uh, determines how the molecules which are there at the air liquid interface, how they are arranged, right? How the molecules at the air liquid interface, how they are arranged. Because these molecules, they are not uh, they are not same as the molecules which are in the bulk. In the bulk, the molecules experience attraction forces from all direction, whereas the molecules which are at the surface, there at the air side, there is no attractive force that is pulling. So these molecules which are at the air liquid interface, they experience more force in one direction towards the bulk. So that makes the interface properties very unique. And that property is quantified using parameters like surface tension, surface energy. All right. So in this particular printing method, formation of the droplet has to happen when you overcome the surface tension at the interface of the bioink. All right. So I guess more or less you understood now how the process is going to happen. All right. But I'll go in more details on the sequence of events involved in the bioprinting process. But if you have any questions so far, feel free to raise your doubts before I move forward with other topics. Any
Questions?
doubts?
No,
No
ma'am.
questions? All right, all right. So now I'll go in more detail in explaining how the droplets are forming, all right, from the ribbon, and how the laser is helping in forming the droplets, because that is more interesting aspect, and that is not what we have seen in other bioprinting techniques, right? So if we divide the laser assisted bioprinting into a sequence of events, so we can do that in four ways. So this image basically shows you the first three events that happens, and the fourth one is pretty self-explanatory, that the droplet will just fall on the substrate. All right. So I'll go over one by one. First, there is laser energy, right? That is, as I said, is important for determining what is the volume of the droplet that you'll get at the end, right? Now, how that affects. So, usually the pulsed energy that you use, the laser energy that you use, is in the range of 1 to 20 microjoule per pulse. So, pulsing rate you fix, all right? Let's say you fix it 5 hertz, 5 kilohertz to 100 kilohertz. So different pulsing rate will also affect how much is the total laser energy that is getting deposited on the ribbon. So that is why it is said per pulse. So per pulse, the energy is this much. If the pulsing rate is higher, the energy deposited will be higher. And the laser are usually having a UV wavelength, which are like 193, 248, 266, 355, or is in the near IR wavelength, like 1064. So, these wavelengths, they are towards like lower frequency side, right? So, near IR, obviously the frequency is much lower. So, the energy, you can now understand, is much less, all right? But since you're working with cells or going to work with cells, lower energy laser makes sense, right? The use of lower energy laser makes sense. So here what happens when the laser with certain energy, when it falls on the ribbon, that energy gets absorbed by the laser absorbing material, that is the thin film of gold, titanium, silver that we talked about. So when it absorbs it, it rapidly evaporates. All right. The molecules in the laser absorbing material, they get excited and basically starts moving and um, like evaporates here. It means like it starts to gain a lot of kinetic energy, all right, in them upon absorption of this laser energy. So because of which a plasma gets formed, and that get further manifested into a vapor bubble that basically expands towards the free surface, means towards the bioink layer. Bioink layer is the free surface for the laser absorbing intel. You can say this in this diagram in 1 and 2. So when laser of certain energy falls, it passes through the transparent support, and the laser absorbing interlayer that absorbs this laser energy, the molecules of this interlayer that gets evaporated, they are using the term evaporated, and plasma formation, and that basically forms a vapor bubble. All right, and this vapor bubble, it expands. This is step 2. This vapor bubble starts to expand towards the bioink layer, because that is the free surface. It starts to expand outwards. Like if the surface is like this, the vapor bubble starts to expand outwards. Okay, now you understood why this interlayer is important, right? So this interlayer is important because it initiates the formation of the droplet for the bioink. The next step is this vapor bubble, it should expand and then collapse. But it can do so, like how it will happen. People have understood it by like mathematically as well. All right. So here I have written some points. The the bubble that it is growing, as it is growing at some radius, it will collapse. That radius is called R max here. So if we put the numbers, some numbers to understand the process, people have calculated that the bubble front, basically the apex, the tip of the bubble, it can quickly basically grow at some velocity like 100 meter per second. At 100 meter per second, and within 100 nanoseconds after the vapor evaporation happens, it can quickly grow a lot and reach its maximum radius before it collapses. So when the maximum radius is reached, then it will collapse within like 1.2 microseconds. So this formation of vapor bubble is very fast, all right? So these are all calculated numbers based on some experimental conditions that they have put in some equation and then they have calculated. Now, the size of the vapor bubble is very small, is very negligible when you compare with the thickness of the bioink layer. So the bubble interacts with the free surface. All right. So the size that we're talking about, the vapor bubble that is formed because of the absorption of the laser into the interlayer. So that size of the bubble is very small compared to how thick the bioink is. At R max, that is the maximum radius this vapor bubble can reach, the pressure is very high at its apex. So it can result in formation of jet. So jet means a stream of continuous bubbles can form. And whether this jet will form or not, how basically, yes, form or not, you can understand it by using a dimensionless distance gamma. Okay, so this gamma is defined as the ratio between h and r max. So h is basically the distance between the center of the initial vapor bubble and the free surface. So if this is the initial vapor bubble, so let me expand a bit. So h can be termed as a distance between here and here. This will be h. All right. And R max is the maximum radius that the vapor bubble can reach. So basically, as the bubble will expand, the radius will increase, and then it will achieve a R max value. After that, the vapor bubble will burst. All right. So if you take a ratio between the H and the R max, you will get a dimensionless distance, that is gamma. Now, using this gamma, they have um, explained under which circumstances a continuous stream of droplets will be formed. But before we go into that, we should understand that this gamma is a function of several things. So I told you that how big or how small the droplet will be deposited will depend on the laser energy, right? But this gamma is also a function of other properties like the viscosity, bioink viscosity, the film thickness, how thick the bioink layer is, and the surface tension. So all these four properties will determine this gamma value, and the gamma value will in turn will determine whether we will get a stream of droplets or not. Okay, we will understand the effect of some of these properties using a paper that I'll come to later on as we are discussing. There you will understand the significance of these parameters much more better. But for now, for theoretical understanding, just understand that the jetting process, as you will see later on, will depend not only on the laser energy, but it will also depend on the bioink viscosity, the thickness of the bioink, and the surface tension. Okay, so it is a very complex process, and yeah, it's a very complex process that is happening here. Now, the next step is the jetting. That is when the vapor bubble will collapse, and you will either get a jet of droplets, or you won't get, or you can get a spraying as well. Okay, so three conditions can happen when jet is not formed. This is A, 3A. When jet is formed, means continuous stream of droplets are forming, 3B. And 3C, when you get, instead of getting a one single stream of droplets, you can get spraying of droplets. All right. So that is 3C. These are three conditions that can happen, and it all basically is governed by the gamma value. Okay. You can see they have written, they have basically defined this entire region from 3A to 3B using gamma 2, gamma 1. So these are some threshold values. So you have to cross this minimum threshold, like gamma 2, you have to cross gamma 2 to get into jetting region, but you have to stay within gamma 1 with to remain in jetting region. If your gamma value is greater than gamma 1, then you will get spraying, and if your gamma value is less than gamma 2, then no droplet will be formed. That is what this diagram is trying to explain. The same thing I have written here as well. So for a given laser energy um, of say some pulse rate or something like that, you have to fix some stuff, right, in order to understand the phenomena. So here also they have fixed the laser energy. For that, you get a vapor bubble at the absorbing layer bowing interface. So for that, you can define the jetting phenomena into three scenarios. In scenario 1, 3A, when gamma is less than gamma 2. So gamma 2 is one threshold value. When it is less than that, what happens? So sorry, when gamma is greater than gamma 2. Sorry, when it is gamma is greater than gamma 2, which is in this region. Here, droplet ejection cannot happen. Why? Because the bubble that is expanding, the vapor bubble that is expanding is too weak. That is why. To reach the free surface of the bio ink. All right, which is why it cannot happen. Then in this scenario, the plume scenario, this is called sub-threshold regime, means uh, the vapor bubble could not even reach, it could not even expand much towards the free surface of the bio ink because it is too weak. All right. So this region is gamma is greater than gamma 2. This is the minimum value, and your is like here, right? Just let me quickly check if I've written correct, right? I think it is gamma should be less than gamma 2. Just no, it's fine. Yeah, it's same. Yeah. In the plume region here, what is happening? Gamma is less than gamma 1. All right. Gamma means the distance, dimensionless distance, is less than another threshold value. Now, when that is there, what happens? The bubble expansion is happening so violently that it has overcome the surface tension of the bioink layer. All right, completely it has overcome. That result in bubble bursting very violently and spraying of the bioink over the substrate. This is the plume region. So you can now understand that gamma 1 is the highest value that we should not cross, and this is the gamma 2 is the lowest value that again we should not cross. If we stay within these two, that is gamma should be greater than gamma 2 and less than gamma 1. When we stay within this sweet spot, then only we can expect the vapor bubble strength to be good enough for obviously overcoming the surface tension of the bioink layer, but in such a way that you get a stream of droplets. You do not get a splashing of droplets over the substrate. All right. Now, the last step in the technique is that the droplets will land on the substrate. But depending on the surface properties that you are using, okay, as well as how fast the droplet is moving, that is, what is the kinetic energy of the droplet and droplet viscosity, all these properties will directly affect the morphology of the droplets that have landed on the substrate. And you can see from the morphology that whether there is splashing or spreading phenomena. If there is spreading, then you will see that more and more droplets they have merged with each other. And if there is splashing, because maybe the gap is too high, all right, or the kinetic energy is too high, if there is splashing, then you will see some secondary droplets also getting formed or also getting deposited on the surface. So Now, these properties will impact, lastly, the droplet morphology. So, any questions so far regarding understanding how the laser assisted bioprinting is happening here? I hope understanding the jetting thing was not too complicated for you. If there is any questions, I would expect to come from here only, but I guess the rest of the sequence events make sense. Any questions from anyone? All right. I'll take the silence that you guys have understood. But if you have any questions at any point of time, feel free to unmute yourself and we can discuss more on it. Okay. So, some things that one should keep in mind when using this technique. First is that you can cause cell injury, even if you are not using pressure, but and also you are not using needle nozzle or anything like that. That can cause shear stress because of the needle walls. You can cause cell injury, and the injury can be due to the bioink composition. All right, or it can be due to the light itself. Also, the pressure that the vapor bubble exerts as the bubble is growing, that can also cause harm to the cells. It can cause bursting of the cells as well. The shear stress within the jet. So here, like it is tapering out, the surface tension is overcome and a tapering is happening, and that gets broken off to form a bubble and then it drops. So during that step, some shear stress also gets generated. So that can cause an effect, cause a damaging effect on the cells, and definitely the landing conditions, like how fast the droplet is coming. If it is splashing, then the cells can burst, right, due to impact. All right. So these conditions, these factors can contribute to cell damage in this technique. So routinely people also add glycerol in as a component in the bioink in order to avoid dehydration. Okay, because as we are coating a layer of bioink on a large surface, so surface to volume ratio is high now, so it can allow like quick rapid evaporation of the water content that is there in the bioink. So to avoid dehydration, people add glycerol, but glycerol is often toxic to cells. If you add too much glycerol, it can kill the cells. So people suggest replacing glycerol with methyl cellulose. Then the light that you're using, usually people use UV light, all right? So UV can be very damaging to the cells and it can cause mutation effects and all. And also, cell damage can happen due to mechanical stress factors that is happening here. Like I explained, that bubble due to bubble growth, there is some pressure that gets generated, and also depending on what type of gamma value you have for the process. If it is, as I told, within the two threshold values, then you get a jet. Otherwise, you won't get a bubble at all, or you will get spraying effect. Okay. So those factors also contribute to some shear stress on the cells, and definitely the landing factors means how soft the substrate is, what is the velocity at which the droplets are getting deposited, what is the kinetic energy of the droplets, and the um, thickness of the substrate. So all this stuff are related to the landing factors, and these factors will definitely cause cell damage due to mechanical stress. So this technique, I have this far for the technique. Next, I'm going to take a paper where they are optimizing some of the parameters, processing parameters of this technique, light assisted bioprinting, and they are going to now show us how to do that, how to do the optimization, how to consider one parameter at a time to find the best parameters for the process. And then they're going to show the power of this technique by printing multiple types of cells in different geometrical patterns. All right. So this is the review article that I used for discussing the basics of light-assisted bioprinting or light-assisted cell printing. I'll share the resource with you. So before coming to brief discussion on the research article that I have, if you have any questions on the topics that we discussed so far, feel free to unmute yourself and we can discuss for a bit and then move forward. I myself haven't got the opportunity to work with this kind of a system, but when I was reading and preparing the notes for you guys, I felt that it is a very fascinating technique, and the level of precision that this technique can give you is much higher than the extrusion one or the inkjet one, because here you're relying on the lasers, and the basically laser is going to determine the droplet size. I've read that it can give very very small droplets, much smaller than the inject methods that we talked about. But yes, it's complicated. So the system would be definitely complicated to work with, but otherwise it's really cool. And I couldn't find any recent literature like published in a year or two who are working with this system. Maybe because the system is very costly, so that is why it has not become very user friendly yet and available only in certain labs. So papers that I'm discussing are like more than 10 years old, but the technology still exists, not for maybe bioprinting, but for other type of printing methods. People use this method for printing, use this similar concept for printing metals as well. So that traditional method where they use it for printing metals, that is been adopted or modified for printing cells, by the way. So it's still a technique traditionally being used, but very expensive.
Is it because of the laser it is expensive, man?
Yeah, lasers are very expensive. Yeah, yeah, you're correct.
Is laser expensive, man, first of all?
Yeah, so you need some source, right, to create a very fine laser. So that source consists of very precious metals. That is what makes it very expensive.
Okay, man.
So I guess the method is clear to you guys, how it is happening, how the printing is happening.
Yeah, yes, ma'am.
Cool. So let's move on and discuss a paper where they're using this laser assisted bioprinting in order to first they're optimizing the parameters, process parameters, and then they're using the optimized process parameter to print multiple cell types and also print bit complicated geometry as well. So it's a very fundamental paper, very good for understanding how this technique works. So this is the paper that I'm using. It's published in Biomaterials in year 2010. Okay. So brief introduction. Um, the resolution of the technique, that is how small and how close the droplets are going to be on the substrate. That is basically defining the resolution of this technique. It depends on various parameters like the thickness of the bioink layer that you coat onto the ribbon, the surface tension and the viscosity of the bioink, the wettability of the substrate, laser energy, the air gap between the ribbon and the substrate. So you by now I think all of these terms make sense to you, right? Because you already understood how these parameters are there in the process and how it may affect the resolution. If it's not clear, let me know. Then this technique becomes challenging because you have to control the splashing. You have to control printing to happen in absence of splashing. Means the droplet, it should not break apart into secondary droplets. And also you have to control the size of the liquid droplets. In and like you have to understand how to control the size of the liquid droplets if you want a uniform structure, means all droplets should be of same size. So you have to understand this, or to prevent splashing, you have to basically optimize, and that becomes challenging. So in this study, they are doing three things. First, they are studying the effect of the bioink viscosity, the cell density in the bioink, the laser energy, laser printing speed, uh, its and their effect on cell resolution. Means what is the highest resolution that you can achieve through this laser assisted bioprinting. So they are basically studying the effect of various key parameters on resolution of printed structure that you get using this technique. Then they have also shown that it is possible to print multiple cell type, and they have also printed a tissue like structure using this technique. Okay, so what is the setup that they're using for this study? They're using a laser assisted bioprinting workstation containing near IR wavelength laser with 1064 nanometer wavelength laser. The laser pulse rate is kept constant for all the experiments. It is 5 kilohertz, and the distance between the ribbon and the substrate is 400 micron. That is also kept constant. Okay. The cells that they are using for this experiment is B16 cell line. This is a carcinogenic melanoma cell line, and there is another one, EAHY926 cell line. This is a endothelial cell line. Okay, the bioink, it changes a bit as the experiments are moving on, but the basic components remains the same. So there is a cell suspension. So they are changing the cell type in few experiments. The cell suspension is in the media, DMEM. It is mixed with different concentrations of glycerol. You understand now why glycerol is added to it, to avoid dehydration of the bioink layer. And it is also mixed with sodium alginate. So addition of sodium alginate basically um, varies the viscosity. Okay, it basically varies the viscosity, overall viscosity of the bio. Yes, yes.
Ma'am, you're not moving the slide.
Oh, what's the slide number that you can see right now?
17, ma'am.
17. Oh, what about now? Still 17?
Yes, ma'am. Still, it isn't showing reference on the first
Oh,
page 17.
okay. Let me reshare first, all right? I think that will solve the issue. What's the slide number that you can see?
19, ma'am.
19? Okay. So I was discussing slide number 19. I'll go again, all right? So the laser system that they are using is basically 1064 nanometer wavelength near IR laser, and it has a pulse repetition rate of 5 kilohertz, and the distance between the ribbon and the substrate is 400 micron. So these are kept same for all the experiments. They are using two types of cell lines. One is B16 cell line, which is a carcinoma melanocyte cell line. Okay, it is derived from the skin. And they are using another cell line that is called EAHY926. So this is a endothelial cell line. All right. The bioink, they are changing a bit for different experiments that I'll explain in all the results that I'll show you. But the basic structure remains the same. Like there is a cell type, it is in a suspension form in media, cell culture media, DMEM. All right, it is mixed with some varying concentration of glycerol and some varying concentration of sodium alginate or matrigel or thrombin. So these are biomaterials that not only help in what do you say, maintaining cell viability and all, but also it helps in giving viscosity or this, um, consistency. It maintains some consistency of the bioink. And you know, viscosity is an important parameter when you want to decide whether or not your you will get jet streams or no droplet at all. All right. So viscosity is important parameter here. So to modulate that, to control that, they're adding some biomaterial. How is the ribbon is formed? So ribbon consists of 50 nanometer thick titanium film. It is coated on a glass slide under vacuum. Okay. And over this titanium film, you are coating this bio ink using blade. All right. And in the later experiment, I'll show you that they are also doing live dead assay, where the green colored cells they signify viable cells and the red color cells signify dead cells. So they are also doing that. So one by one, now we'll discuss the results that they have. So in this slide, they are trying to show the influence of viscosity of the bioink and the laser energy deposited on the bioink on the printing resolution. So in table 1, they are measuring the viscosity of culture media, which is supplemented with alginate glycerol and cells. They're using a rheometer to do that, and the experiments that measured the viscosity, they were all done at a low temperature, that is 10 degrees Celsius. Okay, so these are all solutions in DMEM. In 1, 2, 3, so you guys can see the slide, right? I'm at slide number 20. Is it visible?
Yes, ma'am, it is.
Yeah, okay. So in this table number 1, from 1 to 3 there is no cell. All right, there is only different percentage of alginate, and in absence or presence of glycerol, and in culture media DMEM. And you can see with increase in alginate concentration, the viscosity is also increasing. And in second row and the third row, if you observe, addition of glycerol also increased the viscosity. And when you have a mixture containing DMEM, 1% alginate, and cells like 40 million cells, then the addition of cells itself is also increasing the viscosity. So viscosity here is is modulated by changing the alginate concentration, then also by addition of glycerol, and in absence or presence of cells. So viscosity is not constant here, basically. All right. And table 2, you can see that they are trying to, uh, they have measured the diameter of the ejected droplet on the glass substrate as a function of what is the laser energy with respect to what percentage of alginate that they are using. And what we can see, so here there is no cells in the bioink. The bioink is only composed of alginate, different composition of alginate mixed with 30% glycerol. So in all these concentration, glycerol is there. Okay. As you can see, as they are increasing the laser energy, the size of the droplet is increasing. If you follow row 2, where they're using 0.5 weight% alginate, with increase in laser energy, the droplet size is almost increasing. And if you see that if you keep the laser energy constant and just increase the alginate percentage, then what is happening? The size of the droplet is decreasing. So here you can also correlate this result with viscosity. Means if you keep the laser energy constant and increase the viscosity, then the size of the droplet is going to decrease. Were you guys able to follow me?
Yes, ma'am.
And it is also possible to achieve similar size droplets if you play around again with viscosity and laser energy. So if you see this particular cell where the alginate is 0.1 weight% for laser energy of 4.5, and you follow this cell where the alginate is increased to 1% and laser energy is also increased to 9%, then you can achieve similar size of droplets. All right. So here basically in this two cell, the laser energy and the alginate percentage, they are simultaneously varied. But one common trend that you can see is the viscosity is increased. All right. Viscosity is increased in these two cells along with increase in laser energy that resulted in similar size of droplets. So what this result implies is that if you want to change the printing resolution, that means if you want to change the diameter of the deposited droplet for this process, then you have to play around with the viscosity parameter as well as with the laser energy parameter. And there's a common trend that if you increase the viscosity of the bioink, then the droplet that you will get is smaller for a constant laser energy. And if you increase the laser energy for a constant viscosity, then the droplet size will increase. Okay. Then they've also shown how to get high printing resolution for high cell concentration. So if you follow this particular column, here they are printing 50 million cells that is supplemented in medium. It is mixed in medium. In figure A, there is only 10% glycerol. And figure B, there is 10% glycerol mixed with 1% alginate. This means what? The viscosity of the bioink in figure B is higher than the one in figure A. How much higher is it? So they are mixing 1% alginate, right? So the viscosity is higher by close to 100 millipascal per second. Sorry, 100 millipascal second. So, right? So that much higher it is. So when they are using bioink with the higher viscosity, what they see that in figure B, there is no splashing, means you don't see satellite droplets or secondary droplets forming around the structures, which basically increases the resolution of the Olympic circles that are made, right? Whereas in B, whereas in A, splashing has happened, because of which you can see a very rough outline of the circles, because there are some secondary droplets or the satellite droplets that is also present within these circles. All right. So increasing viscosity with a very high cell number can actually impact the overall resolution of the structure here. Okay, as it basically prevents satellite droplet formation or the splashing of the bioink upon deposition on the substrate. Okay. Similarly, they have done another experiment. Now, in this experiment, they have increased the cell number by one order of magnitude. Okay. And they have varied the aperture size as well. Aperture means the numerical aperture, the pinhole size through which the laser is going to pass and fall on the ribbon. That they have varied, and also they have varied the laser energy. So there are three conditions that they are varying, and the effect of these three conditions is summarized using these phase contrast microscopy images. What we see is that as we are using high laser energy with the larger aperture size, the droplets that you get, they are basically merging with each other. And you also get a line which is having much thick width. If you compare this with a 5 mm diameter aperture of the same laser energy, then the droplets are much more individual. Like you can individually make out the droplets. All right. And the line that is formed now has having much less width. Okay. And as you increase the cell number, if you compare the effect of cell number in these two extreme conditions, you see when the cell number is much higher, the droplets are much more close together. They are merging much more. Okay. And also they are much closely spaced as well. Similar type of interpretations can be done for the lower laser energy, that is 8 microjoule. But here in this case, when the uh, aperture size is much less, like 5 mm, in both the case, you don't see any droplets that is getting deposited. Can any one of you try to explain why this might be? A rough guess would be fine. If you guys remember the jetting regimes that we talked about, maybe you can take help from that to try to explain this. Yes, anyone? If anything is not clear so far, please speak up. I'm here to help you guys.
Yeah, it's clear, ma'am.
Is clear? Okay. Um, Again, I'll come back to my question. Can any one of you try to explain why don't we get any droplets for either of the cell number when we are using 8 microjoule of laser energy for a small pinhole size that is 5 mm? Why there is no droplets? What could be a logical reason to explain this situation? If you remember the sequence of events that we were discussing, when the jet will form, when the jet will not form, if you remember that part, yeah.
Ma'am, it is given, right? The higher the energy deposit, the wider the printed cell. Maybe the energy deposit is low. That may be the
Yeah.
reason.
So the energy has to cross a minimum threshold value, if you remember that point, for the droplet to form, right?
Okay.
Yeah. So in this case, the droplet did not form because it was in this region. So if you remember, let me go back to this diagram. Because it was in this sub-threshold regime when the vapor bubble that was expanding was too weak to overcome the surface tension of the bioink layer. All right. So when we are reducing the aperture size as well, so here the aperture size basically uh, showing the lens focusing capability of the lens to for the laser means if the aperture is very small, then not much of the laser light can pass through. Or if the aperture size is quite big, then most of the laser light that is falling on this lens, it can pass through. So basically the focusing capability of this lens. And if we are using very high power laser, so even if the aperture size is quite small, you can expect the resulting laser that is falling on the substrate, it is having sufficient energy for vapor bubble expansion and then jet formation. But you should uh, take care of these two together in order to make sure the focusing capability and the laser energy, these two should be controlled together to make sure that you has to cross the minimum threshold energy value. If you do not, then the droplet will not be formed at all. So in that case, when there was no droplet, it is possibly because the threshold value of energy was not crossed in this case. where they were using a very small aperture and very low laser energy. Okay. Otherwise, the point that I've highlighted here in the box is true. Okay. It's true in both of these cases. You can explain with this point that why the thickness of the printed line for 18 aperture size and 8 microjoule laser is much less than when we are using 16 microjoule of laser energy. You can explain the variation in thickness using this point, right? Here also you can see the cell number. If when we are increasing the cell number, then you see the droplets to be very close by to each other. All right. Is it clear now? The results that I'm showing here.
Yes, ma'am. Yes, ma'am.
Okay. Now they've also shown the effect of the scanning speed on the cell printing resolution. Again, let me go back to that diagram to help you understand what do I mean by scanning speed. So here in this diagram, so slide number 8, there is a mirror. Okay. So that mirror is moving in XY direction. Okay. And that mirror is basically redirecting the incoming laser to fall on a particular point in the ribbon. So faster this ribbon will move, um, so laser is like a single point. It does not know where to go. This mirror is helping. The movement of this mirror is helping for focusing of this laser point at a particular point in XY plane. Okay. Now, what is the impact of fast moving and slow moving? That we will see in that result. Okay. So now I'm at slide number 22. So they have printed lines, all right, line of droplets. And each line of droplet basically shows that they have been printed at different scanning speed, laser scanning speed. And they have basically printed cell at density of 10 raised to the power 8. Okay. And they are loaded with calcine AM, and there is no alginate or glycerol here. The cells are only mixed with media. Calcine AM will help in visualizing the live cells. Okay. So the first image is basically a phase contrast image that helps you visualize the droplets very well. Whereas the same thing, image B, the same parameters and everything. But here you can see the live cells within the droplets. The droplets are not visible, but the cells are visible, right? And for allowing better absorption of the cells, adhesion of the cells, they have coated the substrate, the glass slide, with a layer of matrigel. Okay. Here there is only a glass slide. So what we see is at very high laser scanning speeds like 1600 mm per second or 800 mm per second, the droplets that you are getting that are very much individual, means you can make out a single droplet individually. But the distance between the droplets is increasing as you are increasing the laser scanning speed. So what's happening, if you can visualize, the laser is coming, right? You just switch on and switch off, that's it. But as the mirror is moving so fast, the laser, um, you can say much less of the laser energy or the photons. Yeah, laser has photons. So much less photon particles are getting, reflected by the mirror. So the much less coordinates point will get targeted on over the ribbon. But as we are decreasing the scanning speed, or as we are slowing down the movement of the mirror, then the laser that is coming, the photons that is coming, they are getting much more higher chance to get reflected by the mirror, and more points on the ribbon will get targeted, right? Will get um, the incident photons, and that's why you get more number of droplets at a closer distance. Make sense? You see, when you are comparing the same thing for a higher, like so 400 mm per second scanning speed to 200 mm per second scanning speed, here also you see the distance between the droplets is becoming much smaller because of the same reason that I explained just now. Means more and more of the laser is getting incident over more number of points over the river, because the scanning speed of the mirror is quite less, right? So the more photons will get reflected, and more points on the ribbon will get incident beam, and then you will get more number of droplets. So with this experiment, they are saying that for them 200 mm per second is the scanning speed, which gives them the best resolution for cell printing. Also, if you see in terms of how many cells are there in the droplet, you'll see that for very high scanning speed, the cell number is becoming very less. Means only one or two cells is getting trapped in the droplet with the high scanning speed. Whereas when you decrease the scanning speed, let's say 200 or 100 mm per second, you can see more and more cells are getting trapped. So in terms of cells as well, it is affecting the printing resolution. Is this slide clear to you all?
Yes, ma'am. Yes, ma'am.
Great. Now what they have done, they have tried to print two distinct populations of cell type. So here in this experiment, they are using EAHY926 cell line, which is endothelial cell at the density of 60 million cells per ml, mixed in DMEM, and 1% alginate they are adding to it. They are not adding glycerol in this experiment. So they have stained this cell type differently. So one group of cell is stained with green dye, green fluorescent dye, which is calcium AM, and another group of dye is stained with a diluted LDL, which is a red fluorescent dye. And they are printing it as a concentric circle pattern. Okay. And what they are showing is that the droplets at the interface, they are basically showing some merging, partial overlapping. It's not completely overlapped, but partial overlapping. This means that the resolution means how well you can make out the two rings. That is good. Means the higher resolution is achievable because the two rings are getting less overlap. You can make out the rings very well. Okay, so this technique is able to basically print multiple types of cells at a high spatial resolution. Okay. Lastly, if you want to make 3D tissue structures, then it is also possible using this technique. So here, what they have done, they have printed uh, like a mesh structure where there is parallel and perpendicular lines. So these lines are of the length of 2 centimeter, with the size of each square is around 500 micron by 500 micron. Okay. So for printing this, they are using a bioink. In this case, in left hand side, they are using a bioink without cells, but it consists of thrombin and calcium chloride. All right. So these two are basically the cross-linking agents onto a surface of glass slide coated with a layer of fibrinogen. So wherever this droplet will form on the fibrinogen, the material will get cross-linked and you will get a 3D pattern like this. Okay, as they are showing with an image. And this is the phase contrast image of that particular pattern. You can see how distinctly at such a low resolution you get this pattern. Then they have also printed the same thing with the same composition of the bioink using cells in it now. So they are using 60 million cells with the same DMEM and thrombin and calcium chloride. They have changed the pattern slightly, means they are printing only with parallel lines now, not with perpendicular lines. And what they see that after 24 hours, when they are staining these cells with live and dead assay dyes, they see that after 24 hours, the cells are all live. Okay. And since they're using a quite thick layer of fibrinogen that is around 100 micron, so they have done Z stacking imaging in order to see how the cells are distributed along the thickness of 100 micron. And what they suggest is that in this thick section, all the cells are alive and they're well distributed as a line. Okay. So in this way, you can make 3D tissue like patterns using droplets using this technique. So that's it. I hope this paper helped you understand this technique much in a much better way. I'm done from my side. I'm open to any questions that you may have now. I'm free to discuss it now. Yeah.
Ma'am, what is the edge over of this technique over the other two, ma'am?
So here you're getting very good resolution. Also, you avoid the issues of clogging because you're not using any needle or nozzle here.
That's it, ma'am.
Yeah. Any other doubts?
No, ma'am.
Okay. What about others? Harsha, Vaishnavi, is it you guys have been quiet for a while? Any queries from your end?
No.
No. Okay, great. What about you, Vaishnavi? Is it fine?
Yes, ma'am. Actually, I have to go through the numerical portion which you have discussed. I have doubt in that, but I have to go to it first because at that time my network was weak. Else,
Oh,
everything is clear, ma'am.
okay. Um, but if you want, I can go over the slide that you missed over. Like, you don't have to spare separate time for it. Your doubt will be clear just now. If you can tell me the slide that you missed,
Yes,
I
ma'am. Yes,
can.
ma'am. If you can go to that slide.
What's the slide number? If you remember, do you remember the
Ma'am,
slide
it's
or the
before
topic?
paper.
Before paper. Okay, before paper. So, Any hint which part you missed?
Ma'am, it's yeah, this slide, ma'am.
This one, where we're discussing the sequence of events. This one.
Yes, ma'am.
All right. So here in this slide, I was talking about the second event that is that happens in this bioprinting technique. So first one is basically the deposition of the laser on the ribbon, as a result of which the layer between the bio ink and the support, that is the interlayer, that interlayer absorbs the laser energy, and it gets evaporated and forms a vapor bubble. Okay, now this vapor bubble has to expand. Okay, so the expansion of this bubble and ultimately the collapse of this bubble will result in the droplet containing bio ink with cells in it. Okay, so some numbers have been calculated to help you understand how fast or how big this bubble can get. So if you look at the point B, it says that the bubble front, that is the apex of the bubble, it can quickly reach its peak velocity, that is 100 meter per second. It should be, I think, mm. I don't know, but it can reach at this peak velocity within 100 nanoseconds. Like within nanoseconds, the bubble can reach its peak size, and the size can be approximately 1.2 micron. Okay, so it's like it's one, and sorry, it can reach in its peak size in 1.2 microseconds. So this peak size is called R max. After this size is reached, the bubble will collapse. The size of the vapor bubble that we're talking about is very negligible when you compare it with the bio ink thickness that you coated over the ribbon. But the bubble has to reach this R max in order to interact with the free surface of the bio ink. If it does not, then the droplet will not be formed. In order to help us understand uh, what do you say, whether jetting will happen or not, whether a stream of droplet will happen or not, they use a dimensionless distance that is called gamma in order to explain the phenomena. So what is gamma? Gamma is a ratio of H and R max. So R max, is the maximum radius of the bubble to that it has to attain, after which it will collapse. That is R max. Whereas H is the distance between the center of the initial vapor bubble and the free surface of the bioink, that is H. Okay. As H will grow, the bubble size will increase, and then it will come a point when H will become same as R max. Okay. And in that way you can basically quantify the value of gamma. And gamma here will determine in which of these jetting regime the ultimate phenomena will fall into. So it says that this gamma is not a simple function, it's a complex function because it depends on various process parameters. First is the laser energy intensity, which I already told you that you need minimum amount of energy uh, that has to be crossed. Okay, and after which the volume of the deposited droplet will be directly proportional to this laser energy. Okay, then the viscosity of the bioink will also determine the gamma value, the film thickness, uh, how thick the bio ink film is, because that will affect the H value, right? And the surface tension. So surface tension, if it is very high, then it will be very difficult for the droplet to form. Okay, so all these parameters affect the value of gamma. And quickly, if I were to explain how the gamma is getting changed and how the three regimes are defined, if gamma lies if it is greater than gamma 2. So gamma 2 is one threshold value. If it is greater than that, then you will get a sub-threshold regime. Here, what is happening? Here, the vapor that is forming, vapor bubble that is forming is very weak, because of which it does not expand well towards the free surface of the bioink. If it is, if it does not expand, then the droplet will not be formed. So in this regime, sub-threshold regime, the droplet will not be formed. Whereas when gamma is less than gamma 1, here what is happening, the vapor bubble that is getting formed is it is forming at a very violent rate. Okay, it is increasing in size at a very high speed. Okay, and it reaches the free surface of the bioink very quickly. So as it burst, then the bioink, that is the layer of the bioink that is outside the vapor bubble, it basically breaks apart into tiny splashes, tiny droplets, like that basically gives us a spray of bio ink. You don't get a single droplet, you get multiple droplets that looks like it is spraying on the substrate. Okay. Whereas in order to get good resolution in your printing process, you want single droplets to be formed every time, as a or they can form at a very high speed, or you can modulate other parameters that we have discussed in the paper as well, like the scanning speed and all, to make sure that droplets are deposited individually with containing single or more cells, or the droplets can be like spaced very close to each other. So that can be taken care of by this changing the scanning speed. But if you keep gamma in between gamma 2 and gamma 1, which are the two threshold values, then you can get a single stream of droplets. This is the regime that is most desired one. Okay. Vaishnavi, I think you disconnected for a second,
Yes,
but is the slide that you missed, is it clear now? The concept that
Yes,
I
ma'am.
tried
Yes,
to.
ma'am.
Okay. Yeah, great. So I guess now for all three of you, the topic is pretty much clear. But if there is any doubt later on that you feel after the class, I'll share the notes and recording with you that you can have a look. All right. I hope you guys have a nice week. This is holidays, but yeah, in India it is not. So, but Merry Christmas to you guys. And okay, it was nice talking to each one of you after such a long time. And I'll see you again on Saturday. I hope you guys come on Saturday, because in that class we will discuss the fourth type of bioprinting, where they're using VAT of bioink solution. And here, there also we are going to use light. Okay. But how it is different from this one, we'll come to know in the next class. For that, you have to come. Okay. Any ending notes from any one of you?